All right, so last Friday we finished up talking about the various intermolecular forces, and we said that on a scale of weak to strong, dispersion forces are typically thought of as weak, and it's an attraction between two nonpolar molecules where there's no net dipole. And then as we increase the intermolecular forces strengths, we go to dipole-dipole. That's the interaction between two molecules that have an overall net dipole. Followed by hydrogen bonding. That's a unique type of dipole-dipole where you've got a hydrogen on the phone, meaning the hydrogen's covalently bound to fluorine, oxygen, or nitrogen. And then we said after that, you've got ion dipole, where you've got some sort of cation or anion surrounded by a molecule with a net dipole. These are pretty strong. And then last but not least, we've got ionic bonds that are the strongest intermolecular force of them all, and it's a very strong attraction between a true cation and anion. Are there any questions with the strength rating for these? This is just a rough guide. It's not an absolute one.
So what would be like an example of ionic bonding that's like between molecules? Because usually ionic bonding isn't that to make a molecule?
So an ionic bond isn't really a bond so much as an attractive force between a cation and an anion. That's really all I'm saying here, is that attractive force for ions is really, really strong.
Ionic bonding between a metal and non-metal?
No, it's the same. So with ionic bonding, it's kind of unfair to call it bonding, right? Because usually with bonding we think of sharing of electrons, but that's a covalent bond. An ionic bond's really just an attraction between opposite charges. That's all it is. So let's do some practice problems. And last Friday we said stronger intermolecular forces lead to higher boiling points. All right, so I'll give you guys a pair of molecules, and I want you guys to help me determine which one has the higher boiling point. Nope. And these two have the exact same molecular formula. They're both C2H6O. Which one do you think has the higher boiling point and why? I think the one on the right does? Why? It looks pretty nice. So you're doing a gut instinct, Paul?
Yeah.
What do you think?
It is the one on the right because the hydrogen is bonded with the O.
Yeah, exactly. So if we look over here, this hydrogen is on the phone, right? It's covalently bound to a fluorine, oxygen, or nitrogen. That means that this can hydrogen bond. Can this one hydrogen bond? Why isn't this hydrogen capable of hydrogen bonding? It's bonded to a carbon, not a direct bond to an oxygen. So this one has no H bonding. All right, if we look at the molecule on the left, do you think it's polar or nonpolar? What do you guys think? Do you think all of the net dipole or all of the individual dipoles are canceling out, or do you think there's a net imbalance? Net imbalance, right? If we look at this one, there's a net imbalance towards this oxygen. So the main intermolecular force for the molecule on the left would be dipole-dipole. And this would be versus H bonding. That means that this one should have the higher boiling point. And in fact, if we go through and we look through the literature, we'll find that ethanol, the compound on the left, has a boiling point of 65 degrees Celsius, where dimethyl ether, the compound on the, ethanol is on the right, dimethyl ether on the left has a boiling point of negative 24 degrees Celsius. So this will boil well below room temperature. So we can predict the rough boiling points of compounds. Let's try another one. Let's try NaCl versus Cl2. Which one should have the higher boiling point and why? NaCl. So what's the main intermolecular force for NaCl? It's ionic, right? What about with Cl2? Is it going to be dispersion? Is it going to be dipole-dipole? Is it going to be ion-dipole or ionic? Can't be H bonding, there's no hydrogen. Dispersion, right? So Cl2, even though chlorine is fairly electronegative, it's pulling on itself. So this would be dispersion. So in this case, sodium chloride should have the higher boiling point. In fact, its boiling point is well over 1,000 degrees Celsius. It's got an incredibly high boiling point, where chlorine gas has a boiling point of negative 34 degrees Celsius. So we can really tell the difference. Let's try another one. Let's try CH4 versus C8H18. So methane versus octane. Octane, you might see octane listings on gas stations when you fill up your car. It's a hydrocarbon. Which one do you think will have the higher boiling point? CH4? Well, let's go through first and identify the main intermolecular force. So for CH4, is it going to be dispersion? Is it going to be dipole-dipole? Can it hydrogen bond? What do you guys think? Dispersion. The difference in electronegativity between a carbon and hydrogen is super duper small. So it's going to be dispersion. There's no net dipole. What about on the right? It's going to be dispersion too. It only has carbon and hydrogens, right? So now we're stuck, right? They have the same intermolecular forces. But what did I say was special about dispersion forces? We said with geckos that they can use dispersion forces to climb, but that all depended on what? Surface area. Which one has more surface area? Yeah, the one on the right has way more surface area. Okay, so this means that this should have the higher boiling point. And in fact, this one boils at about 125 degrees Celsius, where the one on the left boils at negative 162 degrees Celsius. So you can see dispersion forces rapidly scale up with surface area. Does that make sense? So a lot of these you just have to go through. First, identify the main intermolecular force, determine which one's stronger. Whichever one has the stronger intermolecular force is going to have the higher boiling point. All right, so now let's talk about solutions a little bit. This will be our last bit. We already talked about solutions, and what was the unit we used to describe concentration? Anybody remember? Moles per liter, also known as molarity, right? What was your question?
So for the, is surfaces, like, let's say each one is dipole, or ionic, or whatever, and they're the same, but one molecule is larger than the other, is it always surface area?
Yeah, in general, if you have a tie, look for the one with the larger surface area, and that will have the higher boiling point. That's a good question. All right, so with forces in solution, we said we can measure concentration using moles per liter, also known as molarity. And it's really easy to predict what molecules are going to be soluble in a solvent, right? And the typical way of remembering this is that like dissolves like. So molecules with similar intermolecular forces tend to be soluble. Another way of describing this is we describe them as miscible. Miscible just means that they mix evenly, right? So let's describe this another way. If the IMF, the intermolecular force of the solvent, is similar to the IMF of the solute, then they will mix. Another way of thinking about this, if they are different, they form layers. And I should really rephrase this, if they are very different. Sometimes if they're close enough, they will mix, but if they're very, very different, it's very unlikely that they will mix. But this is all based on the like dissolves like principle. So let's take a look at some common ones that you guys maybe have seen around your house. So on the left-hand side, right, we've got oil being poured into gasoline. So both oil and gasoline are all made up of CH hydrocarbons, right? So typically both are considered CXHY, where X is some number. That means they both have dispersion forces. That means they will mix. So if you ever have to use an old lawnmower or chainsaw, you actually have to prep your gasoline mixture by mixing in a little bit of oil. And it doesn't form layers. Everything should mix fairly evenly. What's the image shown in B? What do you guys think that is? Oil and vinegar, right? Like if you go to an Italian restaurant, you get that. If you get salad dressing, you see it separate out. The oil is a hydrocarbon. It's CXHY typically. And vinegar is something very different. And I'll draw out vinegar real quick. So if we look at oil, what's the main intermolecular force for oil? Dispersion, right? So I'm just going to go through and draw this down here. What's the main intermolecular force for vinegar? H bonding. These are really, really different intermolecular forces, right? H bonding is way stronger than dispersion forces, which is why they don't want to mix with one another. And that's why you get the two different layers, right? All right, if we look at C over here, we've got glasses of wine. If we think about what wine's made up of, it's made up of two main components. It's made up of water. Typically wine's about, what, like 90% water? What's the main intermolecular force for water? H bonding. And then the other one that we get is ethanol. That's the alcohol that you drink. And let's draw out ethanol real quick. We already did this once before. What's the main intermolecular force for ethanol? H bonding. So if we look at these should mix because they both have the same intermolecular force. Does that make sense? Okay, there are a couple of special cases, so let's take a look at some of the special cases. Ionic compounds can dissolve in solvents that H bond. Oop. Sometimes. If you go on and you take general chemistry, you'll study solubility rules that go into this in a lot more detail, but for our purposes, consider ionic compounds soluble in solvents that can hydrogen bond. So a good example of this would be salt, sodium chloride, and water. Salt dissolves in water, right? Even though one's ionic and then the other one's in H bonding. So this would be a good example of an ion dipole interaction. So we've got sodium chloride crystals getting surrounded by water molecules. And if you notice, the cation up here, it's really, really attracted to the electron-rich oxygen. So all the oxygen heads are kind of pointed in. Where if you notice this anion, the chloride down here, it's more attracted to the electron poor region, which are the hydrogen. So all of the hydrogen legs are kind of pointed in and surrounding all of the anions. Does that make sense? All right, there's one last example, and then we'll jump into review. I like this example. Soap. So soap is weird. It can dissolve molecules that have dispersion forces and molecules at H bond. And this has to do with the weird property of soap, right? So if we look at the soap molecule on the left, this is something called a micelle, right? It's a big three-dimensional sphere. And on the the outer side, so all of these little circles on the outside, all of these are ionic, meaning they are attracted to polar molecules. So they really want to be close to things like water. However, on the inside, all of these big long chains that are sticking in, all of these are very nonpolar, and they like to dissolve oil. So if we look at the center here, we've got this kind of globby area. That's an oil droplet that's being attracted to the tails that are also nonpolar. So the oil is attracted to the nonpolar tails, but the head groups are ionic and they like to be close to the water. This allows us to basically encapsulate oil particles and get them off of your hands or your dishes or wherever. So this is a unique case. This is something where it's called amphiphilic, meaning it will dissolve more than one type of compound.
Isn't that like very similar to like a cell wall?
Exactly. It's really similar to a cell wall where you've got kind of that fatty membrane region and then you've got different compartments with different properties. Yep. All right, so let's do a couple practice problems and then we'll jump straight into our practice exam. So let's do this first one. The following characteristics. Got a solid state, high melting point, crystalline structure, and soluble in water. Does anybody think they have the answer? So let's first go to solid state. Can covalent molecules be solid? Yeah. Sugar is, we know. Molecular compounds, it's kind of the same thing, right? Ionic compounds like salt, they can definitely be solid. Schematic, doesn't make any sense. So let's cross out schematic. All right, then the next thing says high melting point. What typically has a higher melting point, a covalent compound or an ionic compound? Ionic, right? Which one tends to have a really crystalline lattice structure? Ionic, right? And then which one tends to be soluble in water? Ionic tends to be more soluble. So we would circle ionic. That would be the best answer. All right, let's do a couple more. Which of the following will exhibit the intermolecular force of hydrogen bonding?
H2O.
H2O, right? If we look up here, there's no fluorine, oxygen, or nitrogen, so we can cross that out. Same thing with this one. Same thing with this one. Water is the only one that has a fluorine, oxygen, or nitrogen. All right. Which of the following substances will be the least soluble in water? So what's the main intermolecular force for water again? H bonding. So typically water will dissolve other things that can hydrogen bond, or what was the other case? So water can dissolve things that hydrogen bond or other ions, right? So if we look at sodium chloride, that's ionic. So that's that's very soluble. What about this one? Do you think it's going to be soluble? Yeah, it can H bond for sure. What about this one? No, it's got dispersion forces only, so this would be very, it wouldn't be very soluble. What about ammonia? It can H bond, so that one would be very soluble. All right, I think that's it. So if you guys haven't grabbed it already, grab the practice exam. What I would recommend doing is show all of your work and try to convince your neighbor that you're correct and compare answers with your neighbor.